Hello, welcome everyone. So my name is Juan Pe. I am an independent software engineer and consultant, currently based in Berlin. And I am going to talk about immutable data structures. And I mean, the whole point of immutable data structures is kind of making value semantics scale. So who in this room thinks value semantics are awesome? Hey, almost everyone. That's great. Who here works mainly in a code base where most of the types are value types and most of the functions take things and return them by value? Oh, 2 people. That's awesome. Are you using C++ or Haskell? So that's the thing, right? It's actually complicated to make value semantics scale. So that's why this first part of this talk is called the tragedy of the value-based architecture. And this tragedy starts with a lot of good intentions. So in the center of our architecture, we ideally have a data model that is composed of simple value types, like structs, std vectors, tuples, simple things. Now, the application logic in this software will be pure functions, functions that take a document as value and then produce another document as a value, right? And one of the very often advertised advantages of such an architecture is that then, for example, implementing undo becomes trivial. We just keep the previous states in a vector or in some collection, and we're done. We can now undo. Also, we get concurrency very simply because if we, let's say, want to have a render thread to render the UI in a separate thread, we can just loop in the separate thread with some magical message passing mechanism pass the value of our document to this other thread, and they can do the thing separately, independent from where the other logic is happening. Same thing for, let's say, persistence. I want to save to disk, which might be slow, so I just launch an asynchronous task. I capture the document by value in a lambda and operate with it. Likewise, I can have, let's say, other representations of my document. Like I worked a lot in the music software industry, where you often have like a sonic representation of your document, something that makes audio. And we can follow the same patterns to add this kind of alternative UIs or representations. But there is a problem here. We're doing copies all over the place, right? Like this is not going to scale unless we're really working with trivial documents. So what a smart C++ engineer will do is to say, okay, well, let's not take the document by value and return a new value, which is potentially creating copies, and just take it by reference and do the update in place. But once we do that, we start thinking of our data model not as a value. We're thinking of it as an object, a location, right? Where it is stored in memory becomes important for the correctness of this function. And of course, now these other people accessing the document, they're going to need to synchronize accesses with mutexes and so forth. So we're probably going to add some stateful intermediate representation of our UI with a widget tree. And of course, we need to keep this widget tree updated. So now we need signals and slots in our document so we can call back and update when things change in the document. And of course, we're not going to keep copies anymore in our undo history. So we need to implement this command pattern that is very known to be hard to implement. Doing persistence asynchronously is going to be very hard as well because we cannot simply copy the document, especially after we added the signals. Anyways, our users are already used to having these spinning clocks on the UI, but nothing is going to save us from the flying spaghetti code monster that has taken over our code. So, okay. What was our problem here? Problem actually was copying, right? That's why we went down this rabbit hole. And we're hardwired to think that when you pass by value, it implies that you're going to need to make copies sooner or later. But this doesn't really need to be the case, right? You could think of, I store my value somewhere in the heap, and I just pass a pointer, right? When I need to pass it to someone else. The reason I cannot do that, at least in a world where things are mutable, it's because, well, what happens if my original, the one that passed it to me, now changes this object that is in the heap, right? Now you cannot pass it, mute it, sorry. Now you lose the value, right? The value that goes away under your feet, you could say. So actually, it's mutability that implies that now passing by value means copy. Now you need to copy. But if we remove, mutability from the equation, we could actually also remove the implication. We could simply pass by value by copying a pointer. So this is the fundamental idea behind immutable data structures, which basically work towards tackling this problem. And this is a data structure where all the methods are const. Now, when you want to update the data structure, you can still do it, but you're going to have, let's say, a pushback method that instead of doing the update in place, it's going to return a new copy, let's say, at least from a conceptual point of view, of the vector, which is our example here. We can do this multiple times. We can also, do random access updates like in a typical vector. And we have preserved all the history of operations in the data structure, right? So this is a property that in the data structures world is called persistence, right? Because the old values don't go away. And this means that we can compare previous values from the past, which is very useful in interactive systems, actually, to know what's changed. And this also allows us to have a property called structural sharing, which is basically the idea behind this pointer copying that I mentioned before. These different versions, even though they are logically copies, they don't have to be full copies under the hood. They can share data between these versions. So I really wanted these data structures to exist for a very long time, so I ended up implementing a library myself called Immer that is open source and you can access from that website. And my goal with this library was to first make a library that is idiomatic, because idiomatic for C++ developers. There are lots of attempts of bringing functional programming to C++ that in the end pretend that C++ is Haskell. And I think if we really want to make these techniques mainstream, we really need to make this idiomatic. And also, it has to be performant, because this is in the end the reason we're using C++ and not any of these other higher level languages. And finally, also, and this is tied to performance, it has to be customizable, right? And we have a myriad of techniques like policy-based design and so on that we can use in C++ to make these data structures customizable. And this is particularly useful, for example, to use this data structure, let's say, plug in the allocator from Python and its garbage collection strategy, and now you have like a fast implementation of this data structure for Python as well. So, okay, how do these magical vectors work? And this is going to be the second part of the talk. First, let's try to understand this idea of structural sharing. And the typical persistent data structure that functional programmers use is a linked list, a persistent linked list, where let's say I have a linked list with one element. Now I can create another version by pushing two elements in it. And I get these new nodes with these links. Now, in the original value, I can still call the push front value, the push front operation, right? Oh, sorry, in the new one here, and get a new version, right? But I can still call push front on the old version and kind of get a divergent history, right? Now I have two possible futures, you could say, two alternative variations on operations that we did with it. It's like forking the data structure. And I just created a new node, and most of the data structure is shared between all these values, right? And even though they're conceptually copies, they don't have copies under the hood. Now, C++ developers, we know that node-based data structures like this, with these small nodes, they're not very efficient. So we're going to try to get away from them. But this idea, this underlying intuition, is going to be very helpful down the road. And actually, I point here to a couple of references. If you're interested, there is this book, Purely Functional Data Structures, that really takes these small node-based data structures in combination with lazy evaluation and other things to the extreme and build really interesting data structures. But the data structures that I want to implement are the ones invented by Phil Backwell and popularized by Rich Hickey, who is the inventor of the language closure, which I think is a very bold language because it's a Lisp, which traditionally Lisps are based on lists. And he decided, okay, let's make a Lisp that is going to be based on vectors, on immutable vectors, right? Because vectors are more cache efficient, right? So this is the data structure that we're going to try to build. Now, let's say we want to build a vector. Ideally, we want to have a contiguous block of memory as our underlying data structure. Of course, this is not going to work well in a persistent setting, right? Because if I want to update one of these elements, get a new version with one of the elements updated, I'm going to need to copy the whole block of memory and all the elements in it. But I can make a compromise and say I'm going to split it into blocks. In this picture, into blocks of 4 elements. Now, these blocks are flying somewhere. I need to assemble them somehow. I could use a linked list. No, that's not a good idea. Let's put them in another array. I have the same problem again, and recursively, we split it, and eventually, we get with this perfectly regular tree where every node has a fixed amount of blocks. This data structure is called a Radix Balanced Tree that is characterized by a branching factor that we denote normally as m, which has to be a power of 2. We'll see soon why that is the case. And now you're going to tell me, okay, but this data structure is still a tree. Trees are bad. I mean, that's why STD map is worse than an ordered map. But you have to understand that these blocks, even though in the pictures they are of 4 elements, just so they fit in the slides nicely, in practice, they are of 32 elements. This means that actually, you can have a vector that contains as many elements as you can address with a 32-bit integer, and this is going to be only 7 levels deep. This means that the depth of the tree actually grows slower than other constants that grow that are proportional to your data, right? Like the working set size versus the cache size. That's going to be more important when dealing with a large vector than the depth of the tree itself. So how does this data structure work? Let's say we want to find an element in this tree. Let's say we want to find the element at index 17. First thing we do is we split the index, so we represent it in binary, and we split it in groups of b bits, right? We had a power of 2. We had a, remember our constant m was a power of 2, this is why, right? So we have b bits, and now we can simply go on the next group. We use that to index or to access our root. Then we go down the link in that index. We do that recursively with every block of bits, and we finally get to our element. Now let's say we want to make a version of the vector. We want to update the vector and change this element to a new value. Well, we will first need to copy this block where the element is located. Then we will need to copy the parent. We copy the parent here. And of course, it still has links to some of the other nodes in the data structure, but also to our updated node. We do this recursively until we get to the root. So we actually had to copy one path down to the root to our element, but everything else in the data structure is shared, right? This is how we achieve this balance, in this case, between trying not to copy too much data. We had to copy some data, but still getting nice update performance. So this data structure is already quite interesting, right? It has nice properties, and it has similar properties to a vector from an algorithmic point of view, even though the constants obviously are different. But can we improve? Like a vector, this data structure, for example, concatenating 2 vectors, is going to be O(n) to the second vector because of this little slot here that needs to be filled somehow, right? At the rightmost leaf, we will need to pull in an element from the second vector that we're concatenating, and eventually we will need to reconstruct all the right-hand side of the concatenation. But Phil Bagwell published in a paper alternative in which we allow some nodes to be relaxed. And by relaxed, it basically means we allow this node, this inner node, to have less children than it would normally have if it was perfectly balanced. For this, some of these nodes, they need to, of course, store information about how many children are located in these subtrees. But once we allow the structure to be relaxed in this way, he showed that we can define a concatenation algorithm that works in logarithmic time. And of course, with structural sharing, right? You only copy logarithmic amount of data. With this, of course, then we can also get insertion and erasure at any point. Yes? The question was, do you lose the ability to address it as efficiently? Yes. Still, this concatenation algorithm bounds the amount of extra steps that you need to do. So it's going to be a constant factor that if you measure it in practice, it's like 2x. So it's still reasonable, right? Considering that if you have a lot of amount of data, now you can insert an element at a random position. But yeah, so once we do this, this data structure is the relaxed Radix Balanced Tree. And you get this map of operations, right, where you have effectively constant random access, update, pushback, and slice. This effectively constant means it's actually logarithmic, but as we argumented before, in practice, you can treat it as a constant, even though, of course, maybe a big constant, but it's like a constant. But you have logarithmic concatenation, insertion, and push front, which is great. Also erasure at any point. I've been showing this picture here, but of course, this data structure was invented in languages like Clojure that have a managed runtime and that box the values when they are stored somewhere. So the real picture is this one, right, where every element has its own pointer. As C++ developers, we want a little bit more cache locality, right? So we want to actually store it directly in these nice blocks that I already have in the data structure. The problem is then, what happens if the type T that I'm storing in the vector is big? Now my leaf nodes become big. And this nice property that we had a study of having a reasonable balance between update performance and not, it doesn't hold anymore, right? So I propose a solution for this where, of course, if the T you're storing is as big as a pointer, you just use the same block size. But if you have bigger elements, you simply store less of them in the leaf, but you still store a few of them. So in this case, they are twice as big as a pointer, so they store half as many. Likewise, this also allows us to say if we have small elements, like let's say chars, I can store pack more of them in the leaf. And this is what I call the embedding Radix Balanced Tree, which is characterized by, instead of having just one constant, as I said, it has two different branching factors, one for the inner nodes, another one for the leaf. Now, what is going to be the branching factor at the leaves, where we just compute it to be as many as would otherwise fit in an inner node, right? So with this, we achieve already nice performance in general. There are still cases where things get a little bit tricky. Let's look at this function here. So this function here takes an immutable vector. So I'm using the Immer namespace everywhere here. Nothing is std vector. This is an immutable vector where we push in a loop. We populate it with every integer between first and last, and then return the new updated vector. Can anyone see what's the problem with this function? Sorry? Adding one at a time. And what's the problem of adding one at a time? Exactly. So the answer is there are unnecessary copies, right? We saw that when we updated the structure, we need to update a path down to the root. So in this pushback operation here in the node, we're going to be creating, in the loop, we're going to be creating new nodes that the next iteration of the loop is very probably going to just discard, right? So this is less performant as it could be. So a solution that the Clojure people proposes and we implement in our C++ alternative is to say, okay, I'm interested here. This function is like a transaction, you could say, right? Where I'm interested in the vector that comes in as an argument and the vector that is returned at the end. Everything that happens in between, I don't care if it's doing mutation, right? So we can say, okay, can you give me a mutable view on this vector that is going to use a copy on write strategy, more or less, to mutate the vector in place whenever possible, right? Yes?
Preserve the immutability of the vector. So everyone else who uses it still doesn't see any update.
Yeah, so the question was, do you still preserve the immutability of v, the input value? And the answer is yes, exactly. That's why it's copy on write. It still needs to check, okay, is this node that I'm looking at owned by some immutable thing, right? But as it goes through a couple of iterations, then it will have new nodes that it just created locally, and it will update them in place. When you're done with it, then you say persistent, and you get again a frozen persistent value. Yes?
How do you do traversal? You have to look up each element, or does it try to follow the continuous array?
So the question was, how do you do traversals? Do you look up each element, or do you do go through a continuous arrays? And it depends on which API you use, right? So if you use accessing by index, then you're looking them up each time. If you're using iterators, then it's going to run through one of the buffers. When it's done with the buffer, it's going to go and look up the next one. But there is a third alternative that the library provides, which is using what I call internal iteration, where basically you have a for each function, and you just pass a lambda to the for each function. And in that case, it's going to just run through the buffers as it goes. And it's really efficient. I will talk more about that later. Now, another advantage of this transient API is that now you get also compatibility with the STL, right? Because STL assumes mutable APIs. If you want to reuse an STL algorithm, now you can. But there is something more you can do actually about transients. And then let's look at this function. This function takes a vector and then calls pushback on the vector, and does so a couple more times. Many of you will have noticed the first value is a named value, or L value in C++ jargon. And the second two operations are happening on R values, right? Which are anonymous. They have no one else looking at them. So if you combine this vector with a policy that does reference counting under the hood for garbage collection, you can say, okay, if I have an R value and the nodes I'm looking at from the root only have one reference, no one else is looking at them. I can update them in place. So that's why basically in this library, if you have reference counting, which is one of the things you can choose, actually you can choose other garbage collection strategies, R values are considered transients. And furthermore, this is very nice actually, because now we can go one step further and move V there, the input value there, because we know that it's the last time it's going to be used. And once we do this, we're really using linear types here, if you know about Rust and other like advanced type systems. And now basically transients start to compose, right? So I can call this function twice, pass the return of this function to the next one, and there are going to be, in this whole call, no superfluous copies whatsoever, right? Which means that we achieve a nice property, which is that we're working with this functional-looking, very value-oriented API, yet the performance of the system is going to actually depend on the actual amount of persistent, actual amount of sharing at runtime, right? Which is really nice, actually. So another consequence of this is also that the loop that we had before, if you don't like to use the transient-looking API, you can just move the value, and it's going to have exactly the same performance if you're using reference counting. This is great, but the question everyone has here probably is this fast? Or how fast is this? So I have a bunch of benchmarks that I'm going to skip through to the conclusion. Just say yes. If you really want to look at the benchmark data, I actually wrote a paper about this adaptation of immutable vectors for C++ that was published in ICFP this summer. But I would say like the key aspects here are that, of course, if you do a lot of persistent updates, as we saw, you're doing copies. So that's slower. With regards to iteration, and you asked before, okay, how can you iterate over the data structure? There are these three mechanisms. if you do internal iteration, which most of the time you can, actually the performance is like only 1.5 times lower than on an STD vector. It's really close. I mean, it's unless you're not doing anything interesting with the values, it's almost nothing, right? So that's great. Then the interesting thing is that this data structure allows to organize your architecture in a different way, right? So you get concurrency much more easily. You get undo much more easily, right? So in these ways, basically, even though like the update performance is lower, in practice, for example, latency of the operations in your system will probably get much, much lower, right? Without adding complexity to the code. But I don't really want you to take my word for it, so I want to show you something else. I'm going to show you a example of an application built with this data structure. So I built a text editor, probably inspired by the fact that lately, I don't know, there has been on Hacker News quite a few text editors. There is one from Anti-Res, the guy that wrote Redis, it's called, yeah. That's done in C, and I wanted to show, okay, let's do it in C++ and with a purely value-based architecture. So let's see how this text editor works. I have to look at the screen now, okay. Okay, so I have here a file called Esperanto Wiki. It contains the contents of the whole Wikipedia in Esperanto, like the English one is too big, which is 1 gigabyte. I don't know which text editor you people use, but I can assure you that most text editors really struggle with this file. If you use like Atom or something like that, it's going to crash immediately. If you use Vim, some things might be slow. Let's see what happens here. So I can open the file. Oh, it's immediate. The thing is loading asynchronously. Still responds very fast. Of course, I mean, this is something we could expect, right? Because I can load in a separate thread, load a little bit, and then send the value to the other thread, no mutex or anything, a nice asynchronous loading. There are other things here that are nicer than in the typical text editor. There's one thing that is a little bit stupid, but I really like to comment on it, which is, okay, this thing here, these two dashes on the lower left part of the screen, that is the dirty marker, which almost every text editor has, right? So now if I type, I get an asterisk. Now, what almost no text editor does is that if I delete the characters, pressing the backspace as opposed to doing undo, and I restore the document to its original state, the dirty marker disappears. Why? Because I don't have to anymore check the marker in a stateful way, right? I can simply, since my values are now also easy to compare, I didn't mention that before, but because of this structure, you can see what changed easily between two versions. I never keep a dirty flag in my data model. I just keep my original contents of the file, the current one, and compare them. Is it different or not, right? Now, the other nice thing I can do here is, let's say I'm gonna select all test, press copy. Ooh, I think many text editors will have crashed by now. And now I'm gonna go, I don't know, somewhere, some random position. I'm gonna paste it a few times. No problem. I have now, like, I don't know, 82 million lines of file here. It was immediate, right? And why is this? Well, this is because of the logarithmic concatenation I mentioned, right? So when you insert something in this document, it's gonna be a logarithmic operation, blah, blah. So it supports this. And it's quite fast. Yeah. And I can undo, of course. So I can go back. And it supports Emacs style redo also, so I can edit and then redo, all the typical things. Yeah?
Can you explain that one more time? How you were able to insert that?
Can I explain what? Sorry?
How you were able to insert that so quickly? I didn't understand why you were able to do that.
How was it? The question was, how was I able to insert so quickly? So we will look at that in a second, that this text document is just represented in my data model as a vector of vectors, right? Where it's a vector of lines, basically, right? So when I insert text, I just have to insert something in the middle of this vector. We saw we had a concatenation algorithm that is logarithmic in time. So I can just, and also slicing, maybe that's the other part that is needed for this to work, right? So I can just slice at the point I need to insert, and then reconcatenate, right? With what I had copied, which is also coming from the immutable data structure. So actually, the interesting thing now is that the file might now be bigger than I could fit in my memory if I saved and loaded it again, right? Because this is now relying on a structural sharing. Like a lot of the document is actually the same objects, the same buffers that are appearing in different positions, right, of this otherwise linear sequence. So this is how this works. Go back to the slides. Or I can also, just for completeness, I can save the document asynchronously. I can even edit while it's saving, right? Yes?
So you run out of memory while trying to save, but if you stream your savings, then you
yeah, sorry. Trying to save is okay. What is not okay is to then load it again. Because then, of course, the file doesn't include any information about the sharing, right?
Which you could do that unloading. If you find things that you already have, like if you sort of find correlations, you could just reuse those parts.
Yeah, of course. So that the remark was, you could maybe have do a diffing while loading, such that you find the correlations in the document and try to reconstruct the structural sharing. And yes, you could do that, but I wanted to keep the code simple in this case. Let's go to the slides. That's my view of it. All right. So how does this work? Well, first, let's look at how it doesn't work. This is the typical way you build an interactive application, right? Which is the model view controller architecture. This is what we were trying to get away from in the first part of the talk, right? And the reason is simple. We have this nice separation between model, view, and controllers, but we also have arrows between them. And in this picture, the solid arrows, they represent references, pointers, between these stateful objects, right? And even worse, we also have dotted lines, which represent indirect references, which in this case is there is going to be probably a signal slot mechanism in the data model, so the views can get updated, and I'm going to have a callback that closes over the view, right, to be able to notify. Same thing with the controller and so on. And this is nice. We've been writing software like this for a long time, but what many of us have found when we get to make very large software is that these stateful object trees, they don't compose, right? Like if you modify one thing and then emit, and you want to put this as something bigger, then you cannot get rid of the notification that is happening under the hood and all this stuff. So basically, when you have lots of things, then you have lots of objects and lots of arrows, and you have to think about all of them. You could not abstract them, right? So you get, again, the flying spaghetti monster that takes over your code. So there is an alternative way of doing things that I haven't invented myself. I think people, especially in the web technology space, especially in the front-end web technologies, are really exploring with these ideas, right? Which is what they call, it has many names. So if you do Clojure, it's going to be called the single atom architecture. If you have read about Facebook's Flux, then it's called the unidirectional flow architecture. But the basic idea is to say, okay, I have actions, which is some stimuli that comes from the world. I have the model, which is a representation in computer space of the state of the world. And we have views, which are other representations, more, you could say, good for human consumption, right? And in this architecture, the nice thing is that these things are not objects, or in this stateful sense. These things are values. So we have an action value type, I have a model value type, and a view value type. And the arrows between them, they are not pointers or references between objects like it was in the MVC world. They are functions. So you're going to have a function called update that takes the current state of the world, represented as a value. You take an action, something that happened outside of the world, represented as a value, and you're going to produce, as a result, a new data model, right? Likewise, when we get to the model, from the model to the view, you're probably going to have something like a render function, where you take the model as a value, and then you return a new view as a value, right? This is how React.js works, right? Which is a very popular framework on the web. Now, the problem here is that in C++ we don't have React.js, so what do we do? Well, alternatively, you can use an immediate mode API and just, traverse your document and print it to the screen. And in practice, this works very well, right? Because what you're producing, this view you could consider, well, I'm producing pixels on the screen and my value is indirectly represented by my immediate mode API. One last aspect that some APIs have is then, of course, you need a way to dispatch actions. So there is going to be some framework in which you can have a synchronous thing dispatching actions. But I don't want to get too much into that, because I want to show you this picture. That was the architecture from boxes and arrows point of view. This is the architecture from a code point of view. And this is actually not accurate anymore. So since I added the asynchronous saving and loading, now there is an event loop. But this was like real code copy-pasted from the application before that. And it's an exercise to the reader to see what changes will you need to do to make asynchronous saving and loading to work. But here what we have is, so this is basically, you could say, the main of the application, right? This is the main loop. And in this case, we have a terminal object. Terminal, in this case, it's a representation of the terminal, as in the text terminal that I interact with, right? It's basically a wrapper around ncurses. Then I have the state. This is my data model. So my data model, the core type is called application. That is the root of my data model. And I initialize it, in this case, with the initial contents of the buffer that I load. And I also give it like which key map I want to use. I'm an Emacs user, so I have Emacs-like bindings by default. Then I draw the state, and then I loop. And I loop, basically calling the update function. And as we just said, as first argument, we pass it the current state of the world. As second argument, we pass it the action, which in this case we get from the terminal, right? So the terminal has, in this case, a blocking API that allows you to say, okay, what's the next thing that happened? Whenever something happens, we need to update the state, so update our current view of the model, and then redraw, right? And the nice thing here is that basically this state variable here is the only single mutable variable that really lives through the whole application. And even further, it's hidden within this function, right? So no one is taking a reference to this variable, right? So all mutations that happen, you can understand them by reading this function. There is also maybe one slight API change from the previous slide, which is that here, instead of returning a new application, it returns an optional. It's a way that I used before to signal that the application is done, right? So you return none when you want to exit. The API changes a little bit later when I added a synchronicity. I don't think it's very important to go there in the details. Now, the second thing you need to do to understand this application is to understand its data, right? And basically, here, following like a more functional approach, instead of modeling objects and relations, we start by modeling the data, which is the data that our data model has. So we have some index type that we're going to use for coordinates. And then here we have, this is what I mentioned before, the text, right? This is the meat of what makes this application work efficiently. So we have a flex vector. So flex vector is the name in my library of the vector that supports logarithmic concatenation. You can opt out if you just call it vector, right? And we have lines, which are vectors of chars. We have text, which are vectors of lines. Then we have a file. What is a file? It's a name and its contents, right? The question was, what's a box? So this is a single element container. It's a way to avoid copying the STD string all the time. So it's a box that basically puts const on the API, right? So you can only get a const reference out of it. And under the hood, it's going to share the copies of it, right? So it's going to just copy a pointer. Then the other thing that I have is a snapshot. We're going to use this for undo, right? What information do I need when I undo? I need to know the content of my editing buffer when I did the operation that I want to undo. And then the cursor position, because when you undo, you also want to send the cursor back to where the user was before the operation. So we just store that data. Now we can build the buffer type. The buffer, the term buffer here comes from, I think, Vim and Emacs, this kind of, you could say, like hacker text editor, use the term buffer for one of the documents that you're editing. The first thing we do is keep the file that we loaded. That we saw it's the name and the content. This is how we can see did something change for the dirty marker, right? We have the current contents, we have the cursor, we have the scrolling in the screen. We also optionally have a selection, right? Because I can select text. And then we have a vector of snapshots as my undo history, which in itself, by the way, is again also another immutable collection, right? So I could also keep history of histories if you want to go crazy. And then I have the position in the history, right? So when we're gonna do undo, we're gonna need to know how much did we undo, right? Finally, recursively, we get to the application, which is the root of our data model, which has the current buffer that we're editing and some information about the key map that we're using, the current input sequence, right? Because you can do like Control-C-X, so you need to keep what the sequence of keys that you're pressing is, a clipboard, and some messages that we output. And finally, we have the action, which in this case is this type that indicated what happened in the world. In this case, because it's a terminal application, it's similar. It's simple. The only thing that can happen is a resize or a key press. So that's what we store. And I think like just by reading this data, like most of you can already know and straightforward like implement the application, right? Like if you want to insert a character where you're going to return a new buffer with a character in there and probably update the cursor position and so on and so forth. Yes?
So you're mixing flex vector and vector? Or like not mixing, but like you're calling both. What's the difference?
So the question is, what's the difference between flex vector and vector? Flex vector supports insertion and concatenation in logarithmic time. So it was very handy for the text. Normal vector does not support that. So, but that's okay for the history because the only thing that you're going to do in the history is push back and potentially maybe pop back. Right?
Which you're not doing because you have the history process.
Exactly. I have Emacs-like undo, which I'm going to explain in a second. Sorry, can you repeat the question? A stack. Yes, so the question was, can you use a stack for history? Yes, this is in practice a stack, right? So we're not gonna use the rest of the API. But, well, actually, yeah, we're gonna use a little bit. We're gonna see it in a second how undo is implemented. But yeah, I mean, conceptually, a vector is a stack also if you only use pushback and popback. Yeah. There is another question there?
How is the box of a string different from a share pointer to a const string?
The question was, how is the box different from a share pointer with a const string? And it's almost the same, actually. So the difference is that box has maybe a nicer API, so you can easily, let's say, it has, for example, a method update that is going to give you, you can pass it a function and return a new value that changes the thing inside. Also, it supports memory policies. So this library has this notion of memory policies in case you don't want to use reference counting, for example, or if you want to use single-threaded reference counting and all these things. But yeah, it's like having the share pointer, but with an interface that gives you a value-based API as opposed to a pointer API. Okay, so just to show you one last thing, let's look at how do I implement a feature. And I want to show you how to implement undo, because it's one of the things that in the typical mutable world is quite complicated. And I said before that I implement Emacs-like undo. So for those of you that don't use Emacs, I'm going to explain you how undo works in Emacs. Because the goal in Emacs undo is to basically be able to undo the undos. So you can always redo and never lose history. So basically, there is only an undo operation. There is no redo. So I do an edit. This means that I have a state that is produced by this edit. And I have this cursor here, which is the history post. This is this variable we saw before, the history position. Where in the history am I looking at? Now, when I do more edits, I push more states. And of course, the history position is always at the end. If you remember, if you were paying attention, the history position was an optional. When the optional is known, it means it's at the end. That's how we indicate this. You can do this a few times, more times. Now, let's say I want to undo, where if I undo, I'm going to replace the state by what was there before, right? So I'm going to basically replace the current contents of the buffer by S3, and I'm going to move the cursor back. Now in Emacs, what happens is that when you undo something, the undo action itself gets pushed as a new state in the undo history. I can undo a few times. As I undo, these states here get pushed back again there. And now when I do a new edit, of course, the new edited text is pushed at the end, but I also move the cursor to the end of the undo history. This means that basically in Emacs, there is no redo. If you want to redo, you do an edit, and then you undo, and you will get the undo actions as something that you also undo. Do I make sense? So how much code is this? This is all the code for undo, right? And more importantly, this code is totally independent of the actual edits that you do, the actual operations, right? You don't have to know how to insert a character to uninsert the character. Let's look at it, at what these two functions do. The first function is called record, and it gets the old buffer, the buffer before my edit operation, and the new buffer, the buffer after the edit operation. This function is going to be called whenever I try to do an edit, right? And basically what it's going to do first is it's going to look, did the content change, right? Because there might be operations that don't change the buffer, or even operations that sometimes change the buffer, but in this case didn't because you're deleting the first character or something, right? Then if it did change something, we need to record it, so we just push it at the end of the history vector. And then we also compare, okay, did the position of the history change, right? Is the position of the history the same? If it was not the same, I just did an undo. So that's okay. The undo probably has already managed the history position. But if it's the same, we want to bring it back till the end. This is the thing that we saw that happened there. And then finally, well, we return this new buffer value that has recorded the undo. Then when we want to undo, simply we take a buffer. Then we say, okay, give me the index in the history in which we add. If the index is greater than 0, then we take the last state from the history, and we set it as the new state, right? So the snapshot has the content and the cursor position. We set it, and of course the history now, the cursor in the history has moved back. We also store that, and we return it, right? We also see here, like this code is also not weird to the C++ developer in the sense that I'm also using, mutation of structs, right? Like I'm using normal assignments. The nice thing is C++ already gives me the guarantee that because I'm taking this by value and returning this by value, these updates are not going to be visible, right? So I would say this is kind of idiomatic, yet it works nicely from an architectural point of view. So this is pretty cool, I think. I hope you find it cool too. Just for the record, I also, as a, let's say, CppCon present, I merged 2 days ago a new data structure in the library, which is persistent hash maps and sets, which work in a similar way with regards to this like balancing between having like wide nodes in the tree approach to data structures. There is actually a talk tomorrow by Phil Nash, who I think I saw him before, somewhere there. There he is. He's going to talk tomorrow actually about how this magical hash table that is also persistent work. So that's that. There is also another thing that appeared in the title of this talk that I didn't talk about. So I said the data structures were postmodern. Hopefully I will do a lightning talk this evening where I will maybe clarify or obscure some of these topics. Thank you very much. Here are the links to the text editor and the library. I hope you enjoyed it. Thank you very much. And I think we also have some time for questions. So.
Hi.
Hi.
So my question is, first of all, thank you for the talk. It was very amusing and also very useful. What if you have, if you're concurrently editing, you want to be concurrently editing the same model? How would you deal with that? But you don't want to miss updates.
Yes. So. That is one of the tricky things that the data structure doesn't solve for you, right? So this data structure, you could say, has a forking model, right? So I can fork it, create 2 histories. What happens if I want to reconcile these 2 histories, right? And that's up to you, right? Like you have to, in whatever meaning the things that you store in the data structure have, you have to define some merging operation for it. The data structure is not doing it for you. Maybe there could be some things that the data structure could do for you, like I'm considering adding in the future, for example, a way to diff to the structures, which could be done efficiently, such that, you see everything that happened between these 2 forks, and with this information, for example, you can do the merging in a better way, right? Or even it could try also, like I could try to have a merge operation that given a new diff that you produce, then that does the merge. But yeah, I don't think there is a general solution that would work for anyone, anyways. Yeah.
Thank you.
Okay, you mentioned Ralph Hinz's finger trees at the beginning of your talk. Mm-hmm. Have you ever been given talk about actually implementing those? Because they look very marvelous in paper, but the only implementation I ever stumbled upon was very inefficient. And maybe if we implement it in C++ with modern features and pay attention to cache locality and stuff, this may be a killer data structure.
Yes, so you were talking about the finger trees data structure. Yes. That I had a link to the paper. I didn't even mention it, I think. But yeah, that's a very interesting data structure. And as you say, it doesn't have very good cache locality and all this stuff. So I haven't implemented it. There is, though, an attempt to make them more efficient already. There is a paper called chunked sequences or I think it's called theory of chunked sequences, which is basically applying the same principles, but using, instead of only 5 pointers in the node, it uses a buffer also. The only thing with that paper is that it produces only a mutable data structure. So I guess it's open work to apply that idea of using buffers and combine it with persistence. Anyways, I've run benchmarks actually against that mutable implementation, and this like Radix Balanced Tree data structure was anyways faster. But it might be also because that implementation had other defects, or maybe I also did something wrong in the evaluation, because there are some things you could customize. But yeah, if you want to give it a try, then.
Thank you.
Okay. Yes?
Hi, great talk. I was wondering how much you've looked into looking at memory growth of mutable versus immutable fragmentation, like any scenarios where this would not be favorable?
So I haven't done measurements in that regard, right? You're mentioning like fragmentation and all this
updates
stuff
over
of the
time.
heap, for example, right? Because you're doing more allocations
Right.
and all this. I guess, that depends very much also on how you're using, right? Like how rare are your updates versus your reads. I provide some tools to try to alleviate that, actually. So if you're in the default configuration, I also use a pool of buffers to try to not reallocate if there is already a buffer there, and reuse buffers more. But I think that, it's very application dependent. In the particular application of the text editor, I haven't measured anything. But it's an interesting topic.
All right, thanks.
Do the containers support custom allocators? Like, for example, you want to store it in shared memory and, for example, use smart pointers instead of raw pointers?
So it does support custom allocators. It doesn't support at the moment the standard C++ allocator API. So it only supports allocators that have no internal state at the moment, because there are some questions about what to do. Like you're always producing new values, right? So you have to carry this pointer to the allocator with a confluent data structure, which is the technical term for the concatenation. You even get the question of, okay, what happens if I concatenate 2 vectors and they use different allocators? I think you can find compromises and answers to this question. I was too lazy, so I didn't answer them. I think, for example, for the shared memory example, you can do that, right? Because that's a global property that you can encode in the type. And there are a few things you can customize. For example, I also provide policies that already enable using libgc. It's Boehm's conservative garbage collector. And in that case, there is no reference counting. It just relies on that for the garbage collection. That's the
But does it rely on pointers being raw pointers? For example, if you store it in shared memory, you might want to use the boost offset pointer, for example.
Interesting. So at the moment, it's using raw pointers, yes. I haven't looked at that boost library enough to know how would you make that work, actually. So. So the answer here was using allocator traits or pointer traits, which at the moment I'm not honoring. So I guess that would be something you would need to change in the library. I would imagine it's possible probably, but it's not implemented.
Okay, thanks.
Yes.
In the past, I've used like the builder pattern. If you want to have like a person class that has a first name and a last name, and you want to have that immutable, so you can say with first name on an object, and it'll create a copy of that. Do you have anything in your library to kind of help with creating like user-defined immutable data structure or data types, or any recommended patterns for that?
Not really. So as you saw in the text editor, I'm using plain structs, and I'm just relying on the fact that you can copy them or pass them by value. And in my personal experience, this kind of have worked for me, maybe also because I'm used to working in other languages like Clojure or Haskell, where you work with open data more often. I would imagine that if you wanted to use encapsulation, I guess that's what you want to do there, right? Like you don't want to expose the members directly, and encapsulated with const setters, you could build something like that. I haven't really thought about it much, so but it's interesting. If you have some ideas, actually, it would be nice to talk about them afterwards.
Yeah.
Anything else? No. So, well, thank you very much. Oh, there is one.
You mentioned reference counting as a default policy for memory management, and there is also a demo which would concurrently save the file while you're editing it. What kind of pointer incrementation technique you use, like atomic increments or?
Yeah, so it's by default it's atomic, and that's why by default it works in a concurrent setting. You can also change it and say I want non-atomic, right? So, for example, the library has there is already Python bindings. They are not complete, but just enough to prove that you can do it. And in Python, for example, that's not a problem. I use the single-threaded non-atomic reference counts.
Isn't it involves paying the atomic cost on usual editing operations for the possibility of saving concurrently?
Can you repeat that?
Do you involve the cost of atomics on every update which goes in the main thread for the very possibility of doing saving concurrently?
Yes, because you don't really, I mean, you cannot really know when can you do it, right? That's the point of the reference count. It's what has the information about whether you can do it or not, right? So yeah, this is the case here. It's still fast enough. Of course, if you benchmark it, and this is something you can see in the paper, like reference counts have a measurable cost, right? And when you're copying these nodes, you have to touch a few like reference counts, right? Of like quite a few childs. It's still, a constant factor. In this case, I'm pressing a key, and it's maybe going to change it from 1 microsecond to 5 microseconds. It's good enough.
Is there actually a way to do non-atomic updates in some cases, like with transients, or like for some reason when you are not saving, you would not incur that cost?
So I think yes, with transients, you could do that if you combine the two transient strategies, right? So there is the default transient strategy, which is just look at the at the reference count that you have for garbage collection. There is another one, which is okay. Let's say you're using libgc, you don't want to have reference counts at all. So instead, you annotate the nodes with an owner, which is associated to this transient object. That's why I mentioned before, if you want to use move semantics, or if you want to optimize the moved from operations, you need reference counting. You could combine the two somehow, right? And say, okay, I'm gonna, in my transient, annotate things to not do the reference counts increments, but outside, I'm gonna do the atomic reference counts. I'm not sure how much you will save though, because I mean, you still, in the persistent updates, you will still need to do like atomic reference counts, and also when you copy and all this, when you pass by value. But it might depend on your use case, right? Like if you find that this is, for example, a problem because you have, like big.
That's not a problem in a text editor, but this is a problem when you use a lot of threads working on the same set of immutable data structures sharing a sizable common chunk.
Yes, that's the. I mean, it's a potential problem, right? Like you also have actually fault sharing, right? So you could say, oh, my data is immutable, right? So it's very nice for the caches and everything, but then you have this atomic reference count that you're touching, and you're limiting your ability to parallelize, right? But that is going to depend very much on your workload, right? So when are you doing the updates? How do these interleave with the reads from the many threads? So it's very hard for me to give you like a general advice in that regard.
But in that very case, you have a trade-off. You can just clone the data structure, and from the point of view of the user of the library, there would be no difference. You will pay more memory for less overhead in reference counting, for example.
Yeah, exactly that.
Like have a separate working set for each thread.
Yeah.
And do not pay for atomics.
Yes.
For sizable stuff.
Yeah.
Okay. Do you plan to provide this in your library?
Sorry?
Do you plan to provide this in your library somehow?
I haven't thought about it until now, so but if you
okay.
if you want to contribute it, or I would prefer to be use case driven, right? So my first goal is to have like a complete enough set of data structures to have something like a standard library of data structures, right? So now we have hash maps and sets. I haven't implemented transients for those yet, so that's the next step. Then probably ordered collections are going to be useful. Then afterwards, I'm thinking of how they're called, like internalized strings. Like doing something about strings might be nice that you
Ropes,
can use
you mean?
as keys. Sorry?
You mean ropes?
Ropes? No, not ropes. I mean strings like the ones in Python, where basically there is like a global hash table with all the strings in your application.
Intern strings.
Intern strings, right? That's the English word. But this is speculating a little bit. Also, the roadmap might change depending on the users. And if someone also wants to hire me to implement a specific data structure or use case, I'm available as a contractor. So.
Okay, very interesting stuff. Thank you.
Yeah, thank you.